Have we built machines that actually think like people? Honestly, it's the most profound question of our era. As artificial intelligence silently writes our code, aces our bar exams, and composes our poetry, the boundary between genuine human cognition and cold machine calculation is getting seriously blurred. Today, we're exploring the deep technical and philosophical stakes of this illusion.
Okay, let's dive into this explainer. We're going to dissect the anatomy of a mind, contrasting human reasoning with artificial processing. We'll look at exactly where modern neural networks fall short as mere semantic operators, how researchers are building the blueprints for true artificial general intelligence, and finally, we're going to confront the ultimate mystery, the physical reality of consciousness itself.
You know, humans have this deeply rooted tendency to anthropomorphize, to just project our own humanity onto completely non-human things. The source material references E.T.A. Hoffman's classic story Dear Sandman, where a character named Nathaniel falls madly in love with Olympia, but Olympia is literally just a mechanical automaton whose entire vocabulary consists of a single sigh. Nathaniel fell in love with a clockwork doll. And this perfectly captures our historical trap. We see a mind where there's only a machine. We did this decades ago with simple pattern-matching chatbots like Eliza, and honestly, we're doing it today with large language models.
So here's our roadmap for this explainer. We'll cover 1. The illusion of human thought. 2. Failing at core cognition. 3. Bridging neural and symbolic AI. 4. Building cognitive architectures. 5. Achieving true general intelligence. And 6. The consciousness question.
Starting right off with Section 1, the illusion of human thought. Are LLMs really thinking?
According to cognitive science, the human mind comes pre-equipped with what researchers call startup software. This includes innate abilities like intuitive physics, causal reasoning, and a theory of mind, meaning we just naturally understand that other people have their own thoughts and intentions. Contrast this with modern large language models. These things are incredibly powerful, absolutely, but fundamentally they operate on pattern matching, sequence generation, and statistical learning. They're just semantic operators manipulating words based on vast datasets. It's like a brilliant librarian who knows exactly where every single book is, but hasn't actually read a word of any of them. They aren't cognitive agents reasoning from a grounded understanding of the physical world.
Which brings us to Section 2, failing at core cognition. Let's look at where current AI actually falls short.
When researchers tested this, the results were pretty telling. On intuitive physics, like understanding how objects interact in a physical 3D space, the models showed only a super rudimentary understanding. In causal reasoning, they performed somewhat above chance but were totally hindered by a lack of any deeper insight. They literally couldn't infer the invisible forces of cause and effect that a human toddler grasps instinctively. And when it came to intuitive psychology, like predicting someone's actions based on their mental state, the models failed completely. It turns out an AI that can write a flawless PhD thesis still struggles with the physical logic of a toddler playing with wooden blocks. Current AI is completely missing basic intuitive human reasoning.
Let's move to Section 3, Bridging Neural and Symbolic AI, Combining Learning with Reasoning.
This brings us to an absolutely critical concept: neurosymbolic AI. Think of this as a framework designed to bridge two completely different worlds. On one side, you have neural networks. They act like intuitive artists, learning continuously from messy, high-dimensional data, like images and text. On the other side, you have symbolic AI. This acts like a strict mathematician operating in a discrete, rule-based space, using rigid logic, knowledge graphs, and mathematical constraints. Neurosymbolic AI seeks to combine the two, converting those fuzzy learned features into structured representation spaces that a system can actually reason with. Now, what's really interesting about this slide is Professor Henry Kautz's taxonomy. We can see exactly how researchers are classifying these hybrid systems. Notice the integration pathways connecting natural language processing, learning modules, and symbolic representation spaces. Researchers are using everything from probabilistic logic programming to knowledge enhancement layers to literally force neural networks to conform to strict logical constraints and expert domain knowledge. This is the secret sauce for building a system that doesn't just guess the next word, but logically deduces the correct answer.
Which leads perfectly into Section 4, building cognitive architectures, the actual blueprints for true AGI.
We hear about artificial general intelligence, or AGI, all the time. It's defined as a system capable of performing any intellectual task a human can. But crucially, as the research emphasizes, AGI isn't just about the final output or hitting some behavioral goal. It requires a specific modular cognitive framework that genuinely simulates human-like cognition. We have to focus on how it thinks, not just what it does, and that requires a highly structured architecture.
Let's walk through the organs of this proposed digital mind. A true modular cognitive architecture needs a few specific things. First, a perceptual intake layer. This acts like human sensory processing, normalizing raw data into structured internal representations. Second, working memory. Think of this as a short-term scratchpad with limited capacity for ongoing tasks. And third, a cognitive reasoning engine. This is the core problem-solving mechanism where deductive, inductive, and abductive logic are explicitly chained together to form actual, reasoned arguments.
And this brilliantly illustrates the whole concept. In this unified cognitive architecture model, look right at the top, the metacognitive layer. This acts as the brain's conductor. It orchestrates the flow of information between the symbolic reasoning engine and the neural network learning system. It monitors performance, resolves conflicts, and controls attention. This right here is what transforms an AI from a passive tool just sitting around waiting for a prompt into an autonomous agent capable of self-directed learning.
Section 5. Achieving true general intelligence, moving from isolated tasks to general understanding. The researchers hit the nail on the head here. AGI absolutely must be structurally definable. Past definitions of intelligence just focused on observing if an agent could achieve a goal, but the modern framework insists on explicit cognitive modularity. It has to be operationally testable. We need to be able to look under the hood and verify the stepwise reasoning trace. General intelligence doesn't just spontaneously emerge from one massive black box neural network. It comes from the orchestrated interaction of learning, memory, and reasoning.
And finally, Section 6, the consciousness question, being versus doing.
If we actually build this thing, is there anyone home? To answer that, we turn to consciousness-first approaches like Integrated Information Theory, or IIT, alongside theories like Oracle R. IIT proposes that consciousness exists intrinsically when a system has a maximally irreducible cause-effect structure, meaning the whole is fundamentally greater than the sum of its parts. Meanwhile, OR suggests consciousness might actually arise from quantum vibrations within the very nanoscale substrates of our biological cells. But both theories agree on one huge thing. Consciousness is about the physical reality of being, not just the computational output of doing.
This creates a massive distinction between functional equivalence and phenomenal equivalence. Functional equivalence means the machine acts perfectly human. It solves problems, navigates traffic, and writes poetry indistinguishable from us. It's doing the task. But phenomenal equivalence means the machine actually feels it. It has a genuine, intrinsic, conscious experience of making a decision or seeing the color red. Calculating an answer is fundamentally, literally different from experiencing a thought.
So what does this all mean for us? I pose this to you. Once machines become functionally equal to humans, completely passing the Turing test, and operating with full AGI, are they actually conscious? If they tell you they are sad, are they experiencing sadness?
Well, the crucial point is right here in this quote from the IIT framework. It states that if a machine's brain is implemented in a standard von Neumann computer, which, by the way, is what all our modern servers, GPUs, and robots run on, it may be functionally equivalent to us without being phenomenally equivalent in the least. Because standard computers are just pushing electrons through sequential logic gates, they completely lack that dense, unified, integrated physical structure required by these theories. So according to this framework, our current servers cannot support true consciousness, for sure, absolutely no matter how smart the software gets. Which leaves us with this final provocative thought. As we build massive neural networks, map them with symbolic logic, and orchestrate them with complex cognitive architectures, have we actually created a synthetic mind? Or are we, just like Nathaniel staring at his clockwork automaton Olympia, simply projecting our own humanity onto the universe's most complex, giant neuronal lookup table? It's a question that challenges the very nature of intelligence and what it truly means to be alive. Thanks for exploring this explainer with me today. Keep learning and keep questioning.